Alright, today we're going to look at topic 2 of chapter 7, which is modeling real-world situations using exponential equations, exponential formulas, exponential functions. There's two types of exponential modeling. There is growth, which means that the value is growing exponentially. There is also decay, which means that it's decreasing exponentially. So this is increasing, this is decreasing. If we use the formulas, there's one formula for each. They're very close. Just in the growth formula, you add the rate to 1 to create the base of the exponent, and for the decay formula, you subtract the rate from 1 to create the base of the exponent. The base of the exponent in each equation or each formula is referred to as the factor. Okay, so whether it's the growth formula, then it's the growth factor, or it's the decay formula, then it's the decay factor. The initial amount in the formula is A. The rate of change, which is always a percentage, is the R. Before you put it into the formula, however, you do have to express it as a decimal, which means dividing the percentage by 100 to express it as a decimal point. And then T is the number of time periods that pass. You can use these formulas to calculate a specific value after a certain number of time periods. So let's take a look at this first example. Sam owns a $2,000 computer. The value depreciates at a rate of 11.2% per year. What is the value after 5 years, round to the nearest penny? All right, so the important information here. Well, we got 2,000 as our starting amount. The value is depreciating, which means that it's decreasing. And the rate at which it's decreasing is 11.2% per year. We want to know how much it's worth after 5 years. First, we have to decide how do we model this. Is this a growth modeling problem or a decay modeling problem? Since the value is depreciating, which means decreasing, this is a decay model. So we would use the formula y is equal to a, 1 minus the rate to the t power, since it's a decay formula. What this equation is equal to, that's going to be our final amount. A is our initial amount, or value. In this case, it's value. R is our rate, and T is the number of time periods. We have all of this information except for the final amount. We have the initial amount, that's 2,000. We have the rate, that's 11.2%. Now don't forget, this needs to be converted to a decimal. So you need to divide 11.2 by 100. 11.2 divided by 100, create our decimal, 0.112. 0.112. That's the number we use in the formula. And the time period is 5 years. At this point, it's simply a matter of plugging into the formula and calculating. All right, so I'll plug A into the formula. A is 2,000 times 1 minus the rate, which is 0.112, and then raised to the time period, which is 5. Okay, so at this point, we just need to calculate this. We do need to do this using PEMDAS. So the very first thing we're going to do is the parentheses, the 1 minus 0.112. So this is 2,000 times 1 minus 0.112. That's 0.888. 0.888. And that is to the 5th power. All right, so next we are going to do this, we're going to do the exponent. We'll do 0.888 to the 5th power raised to the 5th power, which gives us this. Now, I'm not going to write this down because I don't want to round it. I'm just going to go to the next step, and I'm going to multiply it by 2,000 times 2,000. So this is my value, rounded to the nearest penny. That's 31 cents with a 9 after it, so it rounds up to 32 cents. So 11.04 and 32 cents, $1,104.32. And this is my value after 5 years. All right, so my computer is now worth almost half as much after 5 years, depreciating pretty quickly. Okay, 5 years is not a long time. So this is a pretty quick rate at which it's decreasing. 11.2%, quite a bit. All right, next, Juanita owns an antique car that is currently valued at $20,000. The value is expected to increase at a rate of 3.15% per year. What is the value after 10 years? Round to the nearest penny. All right, so current value, 20,000. The value is expected to increase, and the rate at which it's increasing is 3.15%. We want to know how much is it worth after 10 years. First, we decide what type of model will we use to represent this, growth or decay. And of course, this is increasing, so this is a growth model, exponential growth, which means y is equal to a times 1 plus the rate to the t power. Y will be our final amount. This formula is used to calculate the final amount, or in this case, the value. A is the initial amount, or the initial value. R is the rate, and T is the time period. Our final amount, we do not know that. That's what we want to calculate. Our initial amount is 20,000. Our rate is 3.15%. Do not be fooled that it has a decimal in it. That does not mean that it's in decimal form. It's in percentage form because it has a percent next to it. So we need to turn this into, is that what I'm doing? Turn this into decimal form by dividing by 100. 0.0315. 0.0315. And the time period, 10 years. All right, now it's just a matter of putting them into the equation and calculating. So we got y is equal to 20,000 times 1 plus the rate, which is 0.0315, and we will raise that to the 10th power. So first thing we do is inside the parentheses. So we've got 20,000 times 1.0315 to the 10th power. Now I just want to point something out. This number that is in the parentheses right here, 1.0315, this is referred to as the factor. Okay, just keep that in mind. It's referred to as the factor. All right, next I will do the exponent. So 1.035 to the 10th power raised to the 10th power, which gives us this. Now I don't want to round that, so I'll just go to the next step and I will multiply that by 20,000. All right, and this is what I end up with. Rounding it to the nearest penny would be 33 cents. So this ends up being $27,272.33. Not bad. It's not great. Not bad. It's better than what a car would usually do, and a car usually depreciates in value. So Increasing in value is better for her than for Juanita. Okay, so those are the two types of models we will be using, growth and decay. The assignment on Canvas is simply a worksheet with word problems on it.